Thank you. Good morning to everybody. My name is Melissa Nigro, and today I'm going to talk about observations of the summertime boundary layer over the Ross Ice Shelf, Antarctica, using SUMO UAVs, so unmanned aerial vehicles. And before I move forward, I'd like to thank my collaborators. So we have John Cassano here with us today, as well as Adrian McDonald and Ben Jolly. So the data set that I'm going to show you today was collected during a 2-week field campaign in January of this year. The goals of the field campaign were to observe the atmospheric boundary layer over the Ross Ice Shelf using a combination of SUMO UAVs and 3 AWSs, or automated weather stations. The campaign was run out of the location of the Tall Tower AWS, which you can see here. So this flat white area is the Ross Ice Shelf, and you have the Transantarctic Mountains here. And you have Ross Island and McMurdo Station down here. As I mentioned, we did use a combination of SUMO UAVs and AWSs. The SUMO is pictured over here on the right. It measures temperature, relative humidity, and pressure. And due to the configuration in which we fly the plane, we're able to calculate out both wind speed and wind direction. For the 2-week time period that we were in the field, we had 6 days that were good for flying, and during those 6 days, we were able to fly 41 flights. One of the automated weather stations that we used was Tall Tower. It's pictured in the background here. It's a 30-meter tower with 6 levels of instrumentation. It measures temperature, relative humidity, wind, pressure, and net shortwave and net longwave radiation. The other 2 automated weather stations are called SNOWWEB at AWS, and you can see it pictured here. They're about a meter and a half in height, and they have 1 level of instrumentation. They measure temperature, relative humidity, pressure, and wind. And we installed these about 10 kilometers to the south of Tall Tower and 10 kilometers to the west of Tall Tower. So essentially, this gave us a nice gradient in both the north-south and east-west directions, allowing us to calculate advection. Okay, so as I mentioned, we did complete 41 flights, and I wanted to give you an idea of what a typical flight might look like. So we would start by obviously launching the SUMO, and then we would have it climb up to about 30 meters above the ground. Remember, this is the height of Tall Tower. At that point, we would have it complete an entire circle with a diameter of about 140 meters. This gave us a really good representation of the atmosphere at that 30 meters, and allows us to directly compare our SUMO observations to the observations at Tall Tower. After that, we'd have it climb up to about 100 meters and complete another 140-meter diameter circle. And it would continue with this type of repetition in increments of 100 meters, all the way up to 800 meters, at which point we would land the plane. As is true with all field campaigns and all observation retrievals, there's always some limitations. So this was our goal for each flight. Most flights did look something like this, but we didn't always reach up to 800 meters. And those limitations that we ran into were that the SUMO had trouble tracking its position in wind speeds of greater than 15 meters per second. We also had trouble with clouds. So if we flew into a cloud, we had some trouble with icing. Essentially, we could see the plane was having some problems. We would land it, and we'd find ice on the prop. And then last, battery lifetime. I think that's pretty common for these types of aircraft. Basically, the SUMO is run on a lithium-ion battery. The temperatures in Antarctica are really cold. Essentially, we would get about 20 to 25 minutes of lifetime for each flight off of a single battery. Okay, so before we take a look at any of the actual SUMO observations, I wanted to give you an idea of the general weather while we were out in the field for that 2-week period. So on the left, you have the temperature observations from Tall Tower, and on the right, you have the wind speed observations. The different colors are just indicating the different levels. So red is the top of the tower, and you follow the rainbow down to purple and then black for the bottom of the tower. So and then I should also mention that these black dashed lines are the times that we actually flew the SUMO. So the temperatures were actually fairly mild while we were out there. The temperatures ranged from about minus 13 degrees Celsius to about minus 1 degree Celsius, so it was fairly pleasant. And then the winds ranged from about calm up to about 16 meters per second at the height of Tall Tower there. So you can see we have a pretty nice wind event on the 17th and the 18th. Okay, so now let's look at the actual SUMO observations. And I want to point out before we take a look at these, is that we are really interested in the changes that we see between subsequent flights. So we can take a look at the atmospheric, the structure of the atmospheric boundary layer, and we can see how it changes a few hours later. So we're looking for things such as warm air advection, cold air advection, surface heat fluxes, things of that sort. So on these plots, you'll see on the bottom is temperature. On the y-axis, you have height above the surface. The dark blue line is the actual SUMO observations. And it's tough to see on this projector, but there is a dashed gray line, which is showing you the dry adiabatic lapse rate, just to give you a reference. Okay, so the first set of flights are from January 22nd to the 23rd, and during these flights we had pretty light wind conditions at the surface. So the winds at the surface were less than 4 meters per second through the duration of the flights that I'm going to show you here. So this is on the evening of the 22nd, so we're looking at about 6 p.m. local time. You can see that we do have a mixed layer at this point. It is super adiabatic, and it goes up to about 100 meters. And then above 100 meters, it does transition into a weakly stable layer. If we then move forward to the next morning, so this is now at a little after 9 a.m. on the 23rd, we see that the boundary layer has cooled quite a bit overnight, so about 5 degrees Celsius cooling. So we had some surface radiational cooling. We now have a well-mixed layer with a depth of about 40 meters. And above that, you can see a very shallow or a very small weakly stable layer from about 40 meters to 75 meters. And that's topped with a very strong capping inversion, so about 5.5 degrees Kelvin from about 75 to 170 meters. So kind of a nice structure to take a look at. We also see we had some warming aloft, so we're assuming that we had some warm air advection overnight. Moving forward a couple hours, we're now at about 11:30 in the morning. We see that our mixed layer has warmed. The depth of it hasn't really changed in the past 2 hours. And we see that aloft we have very little changes. So at this point, we're assuming mostly no temperature advection. This is now ahead another about 2 hours, so about 1:15 in the afternoon. Our mixed layer has warmed again, and it's actually deepened. The capping inversion has lifted a little. We think maybe we're seeing some entrainment at this point. And again, we're not really seeing evidence of warming or cooling aloft, so probably no temperature advection at this point. And then, okay. Now we're at about 6:20 in the evening, so this is about 24 hours after that initial flight that I showed you. The mixed layer continues to warm and deepen, but we're not, actually it didn't really deepen from that last one, sorry, and little changes aloft. And so what I think is really cool about this series of flights on the 23rd, so a little bit longer than 12-hour time period, is that we're seeing this nice evolution of this boundary layer. So it's warming, it's deepening, with very little changes aloft. So essentially, we're assuming that we're seeing very little temperature advection over the course of the day, and that most of the evolution of the boundary layer is driven by surface fluxes at this point. So a nice little case study to take a look at, and we're definitely going to dive into it some more. So in addition to looking at the actual evolution of the atmospheric boundary layer, we can also compare the SUMO observations to other data sets and see how well they agree or disagree. And so I apologize, the colors are a little light on this, but this light blue line, if you can see it, are the SUMO observations. These red lines are the tall tower observations, so those 6 levels of instrumentation. And then this green line, which is kind of faint, but maybe you can at least see these crosses, are output from the Antarctic mesoscale prediction system. So that's a numerical weather prediction system that's used fairly widely in the Antarctic for both operational and research purposes. And so if we can understand how well AMPS, so the Antarctic Mesoscale Prediction System is also known as AMPS, if we can understand how well AMPS is representing the atmospheric boundary layer, that's going to have implications both on operations and research. So in this case, we can see that the SUMO observations and the tall tower observations right around that 30-meter mark are in good agreement. So it's nice when your 2 observational data sets match up. They both show that shallow mixed layer, so that's nice. And we see that AMPS, if you take a look at the actual boundary layer down here, misses that mixed layer and actually is showing a surface inversion. So obviously this will be a nice case study to take a look at to see why AMPS is predicting that surface inversion. If we move forward to 6:20 in the evening, again, we're seeing a good agreement between the SUMO and the tall tower, right around that 30-degree mark. They're both showing the super adiabatic surface layer. Again, AMPS is not really capturing what's going on in the boundary layer structure. So again, I think we can take a look at the evolution of the atmospheric boundary layer over the course of this day and try to understand what's going on with the AMPS forecast. Okay, so let's take a look at another set of flights. So this is now the 20th to the 21st. And the surface winds were a little bit more moderate during these flights. So we're looking at 5 to 11 meters per second for our surface winds. And you can see this is on the evening of the 20th, so around 8:30 p.m. We have a really nice stable boundary layer at this point. If we go to the next morning at about 7:15 in the morning, we can see that, again, we had some surface radiational cooling overnight. We now have transitioned from that stable boundary layer into a mixed layer that's about 50 meters deep, and it's topped with a capping version of about 2.5 degrees. If we move forward a little bit, you see that the mixed layer has cooled a bit and deepened to about 100 meters. And we also have some cooling aloft. So this is telling us that we probably have some cold air advection going on. But you'll notice that we have more cooling aloft than we have at the surface. So this is indicating we probably have some upward surface fluxes that are preventing that mixed layer from cooling quite as much as what we're seeing aloft. And so due to time, I'm skipping through a couple flights here, but you see that the mixed layer is now starting to warm. It's little change in depth from what we were seeing before. And now instead of cold air advection aloft, we're now seeing temperatures that are kind of staying more constant. So we switched from cold air advection to kind of no advection at this point. And that warming in the mixed layer is probably still due to the continued upward surface fluxes. If we move forward, we're now about 12:30 in the afternoon. The mixed layer is warming, and now we're also seeing warming aloft. So we've switched from cold air advection to no advection, and now back to warm air advection. And if we move forward to that evening, so I've fast forwarded to about 5 p.m., you see that throughout the course of the day, we had a lot of warming aloft, so warm air advection throughout the day, and the mixed layer has also warmed and decreased in height a bit. But then if we go to about 6:30 p.m., we see now that we have switched to cold air advection, so we have cooling aloft. And then eventually, by about 10 p.m., we have now switched from a well-mixed layer back to a stable boundary layer, which is a really nice transition to see. So then 24 hours, we went from a stable boundary layer to a well-mixed layer, back to a stable boundary layer. And we had cold air advection that switched to warm air advection and back to cold air advection. So again, this is a really nice data set to take a look at. So some of our conclusions, as I mentioned, I think we've seen some nice things in our observations. We've seen both, looked at cases for both weak and moderate winds. We've seen the transition from the stable to well-mixed back to stable boundary layer transitions. We've seen evidence of both warm and cold air advection. We've seen super adiabatic surface layers. And we've seen cases where AMPS didn't do such a great job of predicting the atmospheric structure. And I actually pulled the slides for that second set of flights. But during those flights, AMPS actually did a fairly good job of predicting the atmospheric boundary layer. So we need to take a look at why does AMPS get it right sometimes and not other times. Our next step is to estimate the sensible heat fluxes that correspond to these changes in the structure that we are seeing. Obviously, we want to dive into the comparison with AMPS, and we're going to work with some collaborators at Ohio State for that. And then John is actually going to go back down to Antarctica in September 2015 and fly the SUMOs out at the Pegasus ice runway. And the nice thing about September 2015 is that September is still winter-like conditions in Antarctica. It's still dark and things of that sort. So it would be really nice to get those observations of the boundary layer. I think that's it. If anybody has any questions, I'll leave you some pictures.
Okay, thanks, Melissa. We have time for a quick question, if there is one. If not, I'll ask one very quickly. Do you have any idea about sensor lag and how that may impact some of these profiles?
Yeah, great question. So you'll notice that in all of my profiles, we are only looking at a sense. We didn't look at desense. And so if there is a sensor lag, it should at least be going in the same direction the entire time. So yeah, instruments aren't perfect, obviously. Yeah, great, thanks.